Okay, so forgive my voice. I picked up something and I'm fighting. But the more I talk, the better it gets. So let's just summarize before we dive into these specific statements. Let's just summarize what we know about constant rate of change. Okay, I think that's helpful. So if you have constant rate of change, what do we know for sure? What's one thing that we know if we have constant rate of change?
Change over y over change of x equals k.
Right. You have the changes in the two quantities, corresponding changes in the two quantities, maintains a constant ratio. What else do we know for sure? So these are the things that you memorize, you know, like the back of your hand, right? The three principles. Yes, sir? Good. Change in y is a constant multiple of the change in x. And what was the third thing? Yes, in the back there. Right, so if you pick the same change in x, if you have constant rate of change and you pick this an equal change in x, you'll always get a consistent change in y as well. All right, and so then we last time we built into how constant rate of change results in a linear relationship. So we can keep going here. So like number 4 is, what's the graph of a constant rate of change relationship? Graphs as a line, right? Linear. And if that's true, then what forms do we have? 2 forms of a line that we've talked about. What's one form of a line? The one you're familiar with. Of course, mx plus b, right? So what's the difference between m and k? What's the difference between m and k? Nothing. They're exactly the same thing. M is just kind of what's been used for slope, but we said slope, the value of slope and the value of constant rate of change are exactly the same. And slope is kind of a little unfortunate because it has this connotation of steepness or inclination of the line, but we said it doesn't even mean that, right? It doesn't mean that. It just means the value of the constant rate. So m and k are the same. And then we also have our old y equals new y plus change in y, which is k times the change in x. So that you use the process to write the equation of the line, and this was that result that we got. So new y equals old y plus change in y, where the change in y is k delta x. Okay, so these are all things that are basically true if you have constant rate of change. Okay, let's look at number 1. So if p changes by 5, then q changes by some multiple of 5 that varies. So if p changes by 5, then q changes by a multiple of 5 that varies. What do we think? What does that have to do with? Which of these statements does that have to do with? 1, 2, 3, 4, or 5? Nope. Let's do with number 2. It says we got a change in p. That would be like a change in x. And we're saying then the change in y. Oh yeah, it does have to do with 3. You're right. So 2 or 3, yeah. So if p changes by 5, then q changes by some multiple of 5 that varies. So what it's basically saying is that this number right here varies depending on the starting value of p. What do we think? K. So this is basically saying that k changes. That's what that says. Always, sometimes, or never? Never true. It's saying that given a change in x, to get the change in y, you'll multiply by a number, this constant, but that constant will vary depending on something else. But then that's not constant rate of change. Constant rate of change means that change in y is a constant multiple. It doesn't change. Okay, the graph is linear. Always. The relationship of P and Q could be represented by y equals kx. Sometimes when, what? If what? So we could represent it y equals kx if what was true? If b was 0, right? If b was 0, then we'd have that. So that's sometimes true when b is 0. If b is not 0, then you can't do this. You'd have to have plus b. The relationship quantities P and Q could be represented by this. That's constant rate of change, always. Questions on these four? Okay, next. Okay, if P increases, then Q increases. Why sometimes?
Because sometimes even when P increases, if the constant rate of change is negative, then Q can decrease.
Good, excellent. So if the constant rate is negative, when you get an increase in one, then you get a decrease in the other. That's what a negative constant rate means. It means that your output would decrease when your input increases. Okay, so this is sometimes true, that they both increase together, but that's with a positive rate of change. With a negative rate of change, it would not be true. Okay, the relationship of P and Q could be represented by delta y equals k delta x plus a non-zero value. So basically what you're saying, by adding a non-zero value, you're saying that this is not true. That's what you're saying. You're saying that the change in y is not a constant multiple of the change in x because you have to add something. What do you think? Never true. Never, because that is, if we have constant rate of change, we have that. We don't have that plus a non-zero number. Adding a non-zero number will just negate that very fact that we know about constant rate of change, that delta y equals k delta x. Okay, the ratio of the changes maintains the same value. We all know that, right? Oh, that's the definition of constant rate of change. When the value of P is 0, the value of quantity Q is 0 also. Okay, that goes back to this one here. They would both be 0 if B were 0. If B were 0, then you have the point 0, 0, but not necessarily. So if B is not 0, then that's not true. But if B is 0, then that is true. The relationship of P and Q could be represented by y equals kx plus b. Always. Always. That's the equation of a line. That's our slope-intercept equation of a line. Questions on these? So the rest were pretty consistent. Okay, so I just wanted to talk about those. Okay, so I think we left off last time with this example, right? And so, what did we do? Did we use the process to find the equation of the line, or to find something else? The equation of the line. All right. So let's just so we have practiced this one more time. Let's look at x equals 7. So we have 2 points on our line, and we have constant rate of change, and so let's practice the process one more time. to figure out what the y value would be when x is 7. Okay? So either you're making progress by yourself or you're getting help. But we did this on Friday. You did it in your homework. So you should be getting good at this now. It'll be on your next quiz, and it'll be on the first exam. So if you've been avoiding it, learn it now. Okay? So find the y value when x equals 7. If we have a linear relationship. And then you can get help from the person next to you or help. Okay? All right. How about, what's your name again? Caitlin, did you get it? Well, no, tell me how you did it. You found the rate of change, and just quickly, how did you do that? Is that the numerator or the denominator? So it's the change in y over the change in x, right? And you got? All right, and then what'd you do? Okay, we got that. So we got k. And so now we're ready to start. We're going to try to find this value. So what did you do from there?
I solved for y, which I did y minus 10.44 over 7 minus 5.1 equals 2.4.
Okay, so you're taking a different approach. That's fine. But in terms of the process that we learned, where's Zhao? Did you get this? Using the process, what'd you do first?
I got 2 for y.
Okay, but I want to know, what did you do? So we got the constant rate, and now we're ready to.
Got y equals 10.44 plus 2.4 times x minus 7.
So y equals, what was it?
No, y equals 10.44 plus 2.4 times 7 minus 5.1.
Okay, so we did it all together there. So so that's perfectly fine. So you just went right to step 3. And so what we talked about was getting the change in x first. And so I can represent that like this, a horizontal line like that. And what part of this thing is the change in x? What part of this thing that he did was the change in x? Good, 7 minus 5.1. The final x minus the initial x. And then from there, we got, how do we get the change in y from that? Times it by the rate of change, right? So you're going to take that 2.1 or 1.9. That equals 1.9. And you're going to multiply it by the rate of change, which is then this. That's our change in y. K delta x. 2.4 times 1.9. Which is this whole term right here. And then finally, you've got the old y, which is 10.44. And you're going to add the change in y. And that's going to give us the new y. So, Zhao, what did you get was the final answer?
50.
Exactly? So the y value when x is 7 is 15. Okay, so we want to learn this because, why? Because it puts the symbols to our understanding of things. It applies constant rate of change, and it really reflects what's happening. As one quantity changes, the other is changing with it. And we're putting the mathematics to that. That's why we emphasize this process. Because it reflects how these two variables are changing together. When one changes, the other changes at this constant multiple. And so then you take your starting value, you add your change, you get the final value. Okay? So I want to put a context on this. So same 2 points. So now we got these points here. And we want to let x equals the time in seconds since the camera started to move, and y is the camera's distance to the right of the left-hand basket in meters. So this is kind of hinting at a situation here. Can you imagine what this is talking about? Use my best quick artistry here. Thank you. That one's not good. Drooping basket. Try again. Okay, better. All right. And so what is this about a camera to the left of the right of the left-hand basket? What is this talking about? Yeah, so like you've seen these like at concerts and sporting events, they have cameras on like cables on wires, right? And so they get these really cool views of like the event or the crowd, and then they scan, they scan over the crowd, and so that's what we got here. So we got a camera on a cable. Maybe where am I here? Oh, pen's upside down. Okay, so we got this camera. All right, and it's traveling on a guide wire like this. And so what is the... All right, there we go. All right, and so then what is the... X is the time since the camera started to move. We don't know where it started. And then Y is the distance to the right of the left-hand basket. So that's basically, here's the left-hand basket. So the current distance would be something like this. So this is that's the value of Y. How far it is to the right of the left-hand basket. Okay, so I think last time we got the equation of this line, right? And we said the equation represents every point on the line. Okay, I'm going to do it again one more time. So to get the equation of a line, to practice what we're learning, you pick a point xy. That represents every point on the line. That point xy represents every single point on the line. And then we go through it. What do we do first? Change an x, which would be, so I could use either point that we know. I'll use this one. My change in x was, so what was this point? 2.9 and what? Starting at this point, 2.9, 5.16, ending at x comma y. What is my change in y? Where's Canaan?
You're changing Y.
Where's Canaan? Right here?
Yeah.
So what's our set change in x? So starting at this point and ending at this point, what's my change in x? Good. Final minus initial. You're doing good. So using constant rate of change, then what is the change in y? We know our k is what?
R K would be
Okay. So change in y is?
change in Y would be Y minus 5.16.
Okay, that's true, but we want to use constant rate of change. Use constant rate of change. Delta y is always equal to
2.4 times X minus 2.9.
good. K times the change in x. All right, we'll have someone take over from there. Where is Daniel Travis?
So then the Y is equal to old Y plus the change. It's a change in
Change in what?
change in Y.
Okay, so that's our, this is what we call point slope. Why? Because it comes down to what? A point, 2.9 comma 5.6. 5.16 is our point, and then our slope is 2.4, or our rate of change. That's point slope form. And then if we multiply it out, if we multiply and simplify, we get 2.4x equals, or 2.4x. Did we do this in class, this part? To get 2.4x minus 1.8. So if you add the 5.16 and you add it to 2.4 times negative 2.9, you get negative 1.8. Okay, so then this is called slope intercept form. That's probably the one most of you are more familiar with from before, but you need to know both. Both are legitimate and useful. Okay, both can be used. Given this, you don't have to simplify. All right, you can just leave it at that. That's perfectly legitimate equation of the line. Oh, so when you have, this is a side note, when you have an equation of a line, it represents every point on the line, so that means that x and y vary. X and y vary, so they're variables. So lots of the emails I was getting about the web work, it was asking for the equation of a line, and you just had all numbers in it, which ended up just being that one number equals another number. So that's not the equation of a line, because equation of a line implies that you have varying quantities. That means you need variables. So this x varies, and then y varies with it. So in the equation of a line, we need that x and that y to be a variable, right? Same with this, okay? You need that x and that y so that now you choose a particular x, it gives you the corresponding y. Choose a different x, it gives you the corresponding y. So x can vary and y will vary with it. Okay. So now in this context with the basketball, we have what? X is the seconds and y is meters. What does the 2.4 mean? What does the 2.4 mean? Okay, is the constant rate of change. So that's true. So what does it mean for the situation in terms of the camera and the baskets and the... What's that? Every second it moves 2.4 meters. Agree with that? Yeah, so the units on that would be 2.4 meters per second. And what do we call that quantity? What is that of the camera? What is that about the camera? Velocity or speed? Okay, how do you calculate speed? Speed equals, what's your formula for speed? Distance over time, right? Okay, so is this a corresponding time and distance here? 2.9, 5.16? So find distance over time. And is this a corresponding time and distance? So find distance over time. Go. So find distance over time for this, find the value. Find distance over time for that, find the value. What'd you get for this first one? Nice and loud. 1.77. And what'd you get for this one? Distance over time? 2.5? 0.5. Okay, so this speed is distance over time, and so we got 1.77, then 2.05. So the speed of the camera is changing. At one point it was 1.77, later is 2.05. Is that right? Agree with that? But I thought we said the speed of the camera was 2.4. So we said it was 2.4, and then you distance over time, you got 1.77, and you got 2.05. So not only is it not 2.4, but it's not a constant speed. So where's the error here? What's going on? What's wrong? Something's not adding up. Yes, sir.
Well, isn't the slope the speed?
Isn't the slope the speed? Okay, so keep going.
So why wouldn't you just do that x initial or final x minus or final y over minus y over final x minus x?
So you want to do y final minus y initial over x final minus x initial. And that's different than what we did here. Okay?
What's there is just the quantities. It's not the actual. It's not. I mean, it's just that at that particular time.
Okay.
So it doesn't really represent the rate.
So where did we go wrong in this analysis? Where did we go wrong? Yeah.
G over T is just like the value, and then like 2.4 is like the change in the numbers.
Okay, she's talking about when we did this 2.4 meters per second, is that distance over time? We want to be more specific. We want to be very precise here.
It's a change in distance over change.
Yeah, it's the constant rate of change. So it's the change in our y quantity over the change in our x quantity. And so why is that important? We just proved why it's important. Because if you do distance over time, you get something else. Okay? Like Daniel was saying, those are just values of distance and values of time rather than a change in distance over a change in time. So we need to update our formula here. Speed is the change in distance over the change in time, which is constant rate of change, right? It's the exact same thing. That's our ratio of changes. That's our ratio of changes. Delta t over delta t. So this is not calculating the speed. So this doesn't really mean anything because it's not the change in distance over the change in time. It goes back to this idea that the values of the quantities themselves don't have to be in a constant ratio in order for you to have constant rate of change. What has to be in a constant ratio? The changes, the ratio of the changes has to be constant. So you can have situations, we saw it with the flag, the lowering the flag. If you just took y values over x values, that changes. But that's possible in a linear relationship, like we're seeing here. It's possible in a linear relationship that you don't have a constant ratio of the actual values of your variables, but you have to have that constant ratio of the changes. Okay, so the 2.4 meters per second is the speed, and is the speed changing or staying the same? Staying the same, 2.4 meters per second. It's like this, we got a constant rate of change or a linear relationship. Okay, what about the negative 1.8? Can you have negative distance? Does it make sense? So we got this y-intercept of 0, negative 1.8. Can it make sense in this situation? Yeah. Huh.
Because it's to the right of the left hand. Or it's on the other side.
Yeah.
Or something.
Right. So if we're defining y as to the right of the left-hand basket, then a negative value of y just means to the left, like a number line, right? So it's just like we're going to the left of that basket, it would be negative values of y. So that's fine. So it just means that at time equals 0, where was the camera? Time equals 0, the camera was? 1.8 meters to the left of the basket, and that when our time quantity started, it started moving right at a constant rate of 2.4 meters per second. And then somewhere here, what's the significance of that point right there? So that would be, x would be the time at which it did what? Right in front of the basket. Y is 0, right? So there'd be some time where y is 0. It's right in front of the basket, or even with the basket. And then as more time goes on, it moves to the right. Okay, so we're talking about speed is change in distance over change in time. So we're talking about speed.
Set.
Paul ist der schnellste aus den Blöcken. Jetzt kommt er. Und jetzt ist Usain Bolt nicht zu halten. Nein, er gewinnt. 9,58 Weltrekord. Ein Wahnsinn.
And the cameraman trying to keep up. Okay, so this is the fastest man alive, and you get to live at the same time that he's living, and he's really fast. He just obliterated the world record here with a 9.58 seconds, 100 meters in 9.58 seconds. Okay, so my question to you is, how fast did he run? How fast is he? What was his speed? Go, do it. What was his speed? So he broke the world record in the 100-meter dash with a time of 9.58 seconds. What was his speed? Where's Alonzo? Yeah. Were you able to calculate his speed? And how did you do that? And what is one? Okay, you did 100 divided by 9.58. And what did the 100 represent? 100 is what? Distance? Careful. We're doing distance over time? Change in distance. His change in distance was 100, and then the corresponding change in time was 9.58 seconds. And did you guys get 10.44? Okay, so this is his speed in the race. So let's just focus on that number, 10.44 meters per second. What does that mean, 10.44 meters per second? Yeah.
He's moving at a constant rate of 10.44 meters per second.
Okay, so every second he covers 10.44 meters. Okay, that's what that number means, 10.44 meters every second. Is that what happened? So this reproduces his race here. This is kind of a... So that's reproducing where he was at every point in time during the race. So what do we think? Every second he covered 10.44 meters. True or false? What about the beginning? Does he cover 10.44 meters in the first second? Less, right? And then at the end? He's covering more distance per second than 10.44 meters. Okay, so then he didn't run at this speed. I thought you were telling me this was his speed. It's change in distance over change in time, right? So some of you are saying it's his average speed. Okay, so we want to make sense of this thing called average speed. What exactly is this? Okay, I'll tell you right off the bat what it's not. It is not finding all of his speeds and dividing by the number of speeds like you would your average test score. Okay? Because how many speeds did he run? All of them. How many is that? A lot. I mean, you're telling me his speed is changing. Well, he ran many speeds, like an infinite number of speeds. So we can't add them up and divide by the number of speeds. Doesn't work. So we're trying to make sense of this number, 10.44 meters per second. Okay. Have I shown you my kids?
Yeah.
I have. Emma and Samuel. Okay. Just want to make sure. All right. So we want to make sense of that. So I have something to add to this to help us. So ready? Here we go. We have a new runner. We have a new runner in the race. It's Emma. Go, Emma. She's in the lead. You can beat the fastest man in the world. You can do it. You can do it. You can do it. Oh, it's a tie. Okay, so there's a reason for this. Let's watch it again. Ready? Here we go. Oh no, not that. Okay, here we go. All right, maybe she can do it this time. Go, go, go. Come on, you got him, you got him. Oh, just a little bit faster. All right, so there's a definite reason I am showing Emma running the race that she's running here. So I've got some questions for you. I want you to get a partner and talk through these questions. And we're trying to make, okay, what's the goal? The goal is to make sense of this number, 10.44 meters per second. Okay? So, what did we say? We said, we calculated his speed, we got this number, but then we said he didn't really run this speed. He didn't really run this speed. He ran slower at the beginning and faster at the end. So what does this number mean for Usain Bolt? 10.44 meters per second. That's where Emma comes in. She's trying to help us understand what 10.44 meters per second means for Usain. Okay, go. My own daughter. What about Emma? 100. They both travel the same distance. How many seconds does it take Usain to travel this distance? 9.58. Emma? 9.58. So here's the key. Same distance, same time. What was Usain's average speed? 10.44 meters per second. This is the number we're trying to make sense of. This was his average speed, but he didn't run that speed. He was slower at the beginning, faster at the end. Maybe for a moment or two he was running that speed. But this was the speed that we calculated for Usain. So what does it mean? Anyone want to give it a shot? 10.44 meters per second is what speed relative to Usain? What's that? His starting and finishing speed? Is that what you're saying? No, his starting speed was 0 and his finishing speed was faster than 10.44. The change? No, it's not the change in the speed. Okay, now we're getting onto it. So 10.44 meters per second. What kind of speed is it? It's only one number. So it's a constant speed, right? So that's Emma's speed, right? Emma's running the constant speed that Usain would have had to run to do what? Questions 1 and 2. So it's a constant speed that achieves what relative to Usain? 9.58 seconds, 100 meters. So it's the equivalent constant speed to get the same distance in the same time. It's only one number. When you do this delta D over delta T, you just get one number. That has to be a constant speed then. That has to be a constant speed, covering 10.44 meters every second. But we know he didn't run at a constant speed. Okay, so it must be like his average speed is like the constant speed of another runner who runs the same distance and the same time. That's going to be our meaning for average speed. It's not adding up a bunch of speeds and dividing by the number of speeds. It's an equivalent constant speed to achieve the same distance in the same time. Doesn't make sense. Time to go. All right, so for Wednesday you have written homework, and then you'll what I posted yesterday, and then maybe a little bit of web work. Okay, the written is kind of long. Get started on it if you haven't.